This conference will now be recorded.
Hello students, now I am going to, in this video demonstration, I am going to give a demo on MATLAB for the MATLAB program for sixth experiment. So 6A program is circular convolution using DFT IDFT method. 6B program is Power spectral density of a sequence, that is abbreviated as PSD of a sequence. So for coming to the first program, that is a circular convolution. So all of you know that circular linear convolution is somewhat related to, more related to DTFT, whereas circular convolution is closely related to DFT of a sequence, discrete Fourier transform. So you are employing here DFT IDFT method to perform the circular convolution between two sequences. So method says that take the DFT of the first sequence, take the DFT of the second sequence, multiply the DFTs and store in product DFT and take the IDFT of this final sequence to get back the circular convol sequence. So you are taking the DFT of the first sequence and calling it as x of k. You are taking the DFT of the second sequence and calling it as h of k. Y of k is equal to x of k, that is circular, that is uh, dot product with h of k. Circularly x of k into h of k. So that you will get y of k. So x of k and h of k is stored in y of k. Finally y of n will be equal to IDFT of y of k. So I am sharing the screen now to find the circular convolution of the two sequences. Here we are going to take a two 4-point sequences, then take the circular convolution between two 4-point sequences for the three possible cases. One is namely n is equal to 4, then n is equal to 5 and n is equal to 6. Whenever n is equal to 7, that becomes the linear convolution length. That means suppose you take two 4-point sequences. So you can find 4-point circular convolution, 5-point circular convolution and 6-point circular convolution. These three things you can do. So whenever n is equal to 7, that answer becomes a linear convolution. So this is your circular convolution program for computing the circular convolution between the two sequences. So first of all, CSC as usual, use remind CLC close on and clear off. X1 is equal to input of enter the input sequence. H1 is equal to input of enter the second sequence. So first of all, you are entering the first sequence, you are entering the second sequence. Then L1 is equal to length of x1, L2 is equal to length of h1. Suppose you enter two 4-point sequences, L1 and L2 will have the values of 4 because length of x1 is 4, length of h1 is 4. Then m is equal to max of L1 comma L2. So you are going to calculate the maximum value of L1 and L2, that is 4 actually. Then n1 is equal to L1 plus L2 minus 1. Okay. So you are going to calculate the linear convolution length L1 plus L2 minus 1. Then you are going to use n is equal to input of enter the n value. N is equal to input of enter the n value. That means suppose n value is 4, let us say x is equal to x1 comma 0 starting from 1 to l minus l1. That means 4 minus 4, l1 is already 4, l2 is already 4. So it will have x is equal to x1 comma 0 starting from 1 to 0. That means no zeros are padded. 0 zeros are padded means no zeros are padded. Similarly, h is equal to h1 comma zeros of 1 to n minus L2. N minus L2 value here is once again 0. So no zeros are present in the first case. So like that. So x will be as usual. When you give n is equal to 4, x will be as usual. Then x is equal to FFT of s comma n. You are going to use the FFT command. FFT command is going to compute the DFT of the sequence. FFT command is going to compute the DFT of the sequence. FFT of s comma n, h is equal to FFT of h comma n. Then you are going to use y is equal to x dot star h. Okay, y is equal to x dot star h. That means the difference between x star h and x dot star h already you know. X star h is the product, whereas x dot star h is element by element multiplication. X star is normal product. X dot star is element by element multiplication. We are multiplying element by element and then storing the values inside y. X is equal to FFT of s comma n. It's going to calculate the DFT of x of n. H is equal to f of x this FFT of h comma n. We're going to calculate the FFT of h comma n store in h. Then capital Y. You are using here, be careful that you are using all capital letters here, because we are already used the small letters for this particular variable. You can use another variables also if you want. Instead of using capital letters, you can use another, but it will be an indication. It will be an indication. You should not use one more indication is one more instruction is you should not use x of k and h of k command this representation, because that represents leads to error in MATLAB. So x is equal to FFT of s comma n, y h is equal to FFT of h comma n, y is equal to x dot star h. So we are going to perform element by element multiplication of the two values and store inside y. Then y will be equal to IFFT of y comma n. So you are going to find out the inverse Fourier transform of y comma n, then store inside y. When you take the inverse Fourier transform, you get back the circular convoluted output. So circular convolution output. So for plotting that, you need to declare the three variables. You need to define three time indices. N1 is equal to 0 is to 1 is to length of x minus 1. So suppose length of x is 4 here, so it will 0 is to 1 is to 3 you are going to get. N2 is equal to 0 is to 1 is to length of x. So already we discussed that whenever you are giving a is to b is to c, a is the starting index, b is the increment, c is the end value. A is the start value, b is the increment, c is the end value. So 0 will be the start value, 1 will be the increment value, length of x minus 1 will be the final value. That means because they are integer values, you are going to use 0, 1, etc. 0, 1, 2, 3, this is etc. Okay. Similarly, n2 will be equal to 0 is to 1 is to length of h minus 1. n3 will be equal to 0 is to 1 is to length of y minus 1. So all the things will be defined from 0 to 3. Then you are using a subplot command of subplot of 311, subplot of 312, subplot of 312, 313. Entire screen is divided into 3 rows, 1 column, first position, 3 rows, 1 column, second position, 3 rows, 1 column, second position. So entire screen is divided into 3 rows, 1 column, consisting of the first plot, you are going to plot the input sequence. Second plot, you are going to plot the second sequence or impulse response. Third plot, you are going to plot the output sequence. Here you are using the discrete time signals, so that's why you are using stem command instead of plot. Stem of n1 comma x, stem of n2 comma h, stem of n3 comma h. Directly you can use stem of x, directly it takes the amplitude. Because you have to define the causal sequence, define from 0 to 3, you have to use stem of n1 comma x. Similarly, for the causal sequence h of n defined from 0 to 3, you have defined stem of n2 comma h, or for y of n also it is stem of n3 comma h. So like that, this will be the logic of this particular program. Second case, what you are going to do, all the program is different. Second case, you are giving, once again you are pressing run, and then you are giving n is equal to 5 for the second case. So what happens there? X1 comma 0 starting from 1 to n minus L1. That is 5 minus 4 will be 1. So 1 0 will be padded for x1. So 1 2, suppose you are giving 1 2 3 4, it will be 1 2 3 4 comma 0. Then h value will be h1 comma 0 starting from 1 to n minus L1. So 1 2, once again 5 minus 4, 5 minus 4 will be 1. So 1 0 will be padded for h of n. So x of n will have 1 2 3 4 0. H of n will also have the value 1. So suppose you give h of n as 1 1 2 1, then is 1 1 2 1 0. Like that, you need to give x of n values and h of n values, and then so you are going to 0 pad and then increase the length of the particular sequence. Okay, like this. The third case, what you are going to do, you are going to give n is equal to 6. Then two zeros will be padded. 1 2 3 4 5 6 for the sequence x of n will be 1 2 3 4 comma 0 0. Next, similarly, the new sequence h of n will be 1 1 2 1 comma 0 0. So like this. So third stage case you will be plotting. Fourth case, if we give n is equal to 4, you get the linear convolution answer. Of course, we are not interested in that particular linear convolution because that is different. Already you have performed the linear convolution. You can test that if you want. You can test that by n is equal to 7. You get the linear answer as linear convolution. For n is equal to 7, if you give that particular thing, you get the linear convolution answer. So like that you can give. Okay. So this is about the logic of the program if we discuss. Now I will share the screen for the command window. Let us run this program and then give the inputs. So I have given run here. So now I am sharing the command window. Enter the first sequence is there. You need to enter in the square brackets 1, 2, 3, 4. You can give commas also in between them 1, 1, 2, 1. So it will ask enter the n value. So let us give it as 4. So the answer is displayed as y is equal to 13, 14, 11, 12. The answer is displayed as y is equal to 13, 14, 11, 12. Now I have stopped the sharing the screen and show you the plot. So this is a plot for x of n, h of n and y of n. Okay, this is a plot showing for x of n, h of n and y of n. Okay, 1, 2, 3, 4, 1, 1, 2, 1 and the output sequence whatever you have given, the same thing is plotted. This is for n is equal to 4 that you are going to get. Next, we once again run the program for n is equal to 5 and show the output now. I will once again share you the command window. So now you give the first sequence as first sequence must be given 1, 2, 3, 4. Second sequence is going to be given 1, 1, 2, 1. Enter n value to be 5. Now if you press enter, then what is there? There is all these samples are shown. The command window you are going to see the output. So here remove that semicolon there. Y is equal to if50 of y comma n. The command there you have to remove the semicolon such that all the samples are appearing. So you have given 1, 2, 3, 4. Automatically the sequence is plotted as 1, 2, 3, 4, 0. It will take as 1, 1, 2, 1, 0. So next the circular convolution output is plotted. Output is your samples you are going to get 12, 7, 7, 12, 12. Now let's see the plot for this particular this one. So this will be the plot for the x of n. So here you can clearly see that G10 is paired here for x of n. 10 is paired is for this one. At 4 you are going to see this particular 0. So the output will be different now. It will be going to 5-point circular convolution is returned. Next, the last case, of course, we are going to give the perform a 6-point circular convolution. So by giving n is equal to 6. Let us run the program once again. I will show you the screen now. So give 1, 2, 3, 4. 1, 1, 2, 1. Now you give n is equal to 6. So whenever you give n is equal to 6, the values 6 values will be there. 6-point circular convolution output is returned. It is 5, 3, 7, 12, 12, 11. This will be that. Now let us see the graph now for this. So this will be the graph for this particular thing. So 0, 1, 2, 3 as usual. 4 and 5 zeros are paired. Similarly 0, 1, 2, 3 for the second sequence. 4 and 5 are 0 paired. Last case you are going to see whatever the answer plot you have got, the same plot you are going to see. So like this, for n is equal to 4, so you can perform 4-point circular convolution, 5-point circular convolution, and 6-point circular convolution, return the output. If you perform, you can test at 7-point also, you can get the serial convolution also. So this is about the video, this demo for the 6A program. Now let us give the 6B program demo, that is power spectral density of a sequence. So this is the program for the power spectral density of the sequence. So the power spectral density, how we are going to plot, let us see the logic of this. So CLC close or clear all, T is equal to 0 is to 0.0001 is to 0.6. You are going to take X is equal to sine 2 pi into 50t plus sine 2 pi into 2 pi into 120t. You are going to take these two sinusoidal signals and then you are going to add them. So sine 2 pi 50t plus sine 2 pi into 120t. Then you are going to use subplot of 3 comma 1 comma 1, plot of x label of time, y label of amplitude. Okay, so you are first using your plotting plot of so by taking those values, the sinusoidal signal will be plotted. This is a superposition of two sinusoidal signals. 0 is to 0.001 is to 0.6. Similarly, so the starting value will be 0, the increment value will be 0.001, the ending value will be 6, so 0.6. So like this you are going to plot the input signal. Next is subplot of 3 comma 1 comma, because there are three plots here that are there. First, the entire screen is divided into 3 rows, 1 column, first position, second position, and third position respectively. So plot of x, so plot is a command used to plot the continuous time signals. So x label of time, y label of amplitude, that is, so input signal is plotted in the first position. Next, y is equal to x plus 2 times rand of size of t. So it is going to generate the random of this random noise is going to generate the random numbers, and random is going to random integers is going to generate, which you call this as random noise. Okay. So subplot of 3 1 2. Second position, what you are going to do? You are going to plot this particular, this one, noise corrupted signal. Okay, this is you are going to have this particular this one with you are going to reach zero mean random noise. You are going to take zero mean random noise. So plot of 1000 into t of 1 is to 50, y of y 1 is to 50. That means it is going to take t from 1 to 50, 1000 into t, then 1000 t into 150. Similarly, y will be taken from 1 to 50, like this. So title loss signal corrected with zero mean random noise. So x label of milliseconds, y label of amplitude. Next, you are going to use capital Y is equal to FFT of y comma phi 12. You are going to first introduce, you are going to calculate first x of k and store inside, that is y of k, and then store inside y. Then power spectral density, how do you define power spectral density generally? We are going to define power spectral density as mod x of k or mod y of k whole square. The same thing is done here. We are going to plot pyy is equal to y dot star conjugate of y slash phi 12. Okay, so y dot star conjugate of y slash phi 12. That means already you know energy spectral density formula. It is given by modulus of x of omega whole square. In the same way, when we are discussing about the DFT, it is given by y dot star conjugate of y slash phi 12. Okay, so pause, there is a phi. The phi 12 is, that means you are, because you are going to take that particular phi 12 interval. So the energy divided by that particular interval you are going to take. So that gives the power. So power spectral density. Power spectral PYY, you are going to call it as PYY. PYY of y dot star conjugate of y. Conjugate of y will calculate the this a plus jb is there, a minus jb will be there. Okay, x dot x actually mod x of k, how do you define mod of x of k whole square or mod of y of k whole square? In this case, it is mod of y of whole square, which is defined as y into y conjugate, because a into a conjugate becomes equal to mod a whole square. So a into a conjugate becomes equal to mod a whole square. The same thing you are going to do. Okay. So pyy is equal to mod y dot star with conjugate of y slash phi 12. So f is equal to 1000 into 0 is to pi 256 divided by phi 12. So you are going to divide so many points here. 1000 into 1000 into 0 is to 256 slash 12. So 1000 into 0 by slash 12 and 1000 into 256 slash 12. If that's the frequency range, that's the frequency range for plotting the power spectral density. Then you are going to use the subplot of 313. So third position, the power spectral density graph is plotted. The third position, subplot of 3 rows, 1 column, and third position, this one is plotted. So plot of f comma p y y of 1 is to 257. So title of frequency content of y, okay, and x label of frequency, y label of PSD of signal, x label of frequency and y label of PSD of power spectral density of signal. So like this you are going to take this particular thing. So you have to understand that first you are going to take the superposition of two sinusoidal signals. You are going to plot that, call it as x there, x signal. Then you are going to add some noise there, 0 mean random noise, x plus something, 2 times random of something is going to, that is defined as y. So subplot of 312. Then you are going to plot that particular this one. So second position is plotted. Third position, what is going to plot it? You are going to take the first the x of k, y of k value, call it as y is equal to f50 of y comma 512. Then calculate the power spectral density of that, y dot star conjugate of y slash 512. Then divide that for this frequency points. Then you plot, you use the command plot of f comma p y y of 1 is to 257. So title of frequency content, x label of frequency and y label of power spectral density of signal. So this is the logic for your power spectral density program. Now let us run this program. So there are no input parameters that are there to be entered, but directly the signal will, the program will be executed directly. I will show the result and the output here. Now I will share the screen. So there are no input parameters that will be entered in the command window. Directly whenever you execute run the program, you will get the output. For first signal you are going to see there is a signal, input signal, so superposition of two sinusoidal waves. Okay, so this will be the figure showing the superposition of two sinusoidal signals, sine 2 pi 50 t, sine 2 pi 100t. Then signal corrupted with 0 mean random noise. The second case you are going to take the signal corrupted with 0 mean random noise. So amplitude is so time versus amplitude. X level of time, y level of amplitude. Third one is you are going to see the power spectral density plot. That is, x-axis is you have frequency content versus the power spectral density. So we are going to see that the entire screen is divided into 3 rows, 1 column. First position input signal is plotted. Second position signal corrupted with that 0 mean random noise is plotted. Third position PSD of signal, power spectral density of signal is plotted. So like this, this is your logic of the program for calculating the power spectral density of a signal. So this is the logic of the programs for 6A and 6B. So for the sixth experiment, you will have both the 6A and 6B, both the experiments. One is 6A is the circular convolution, which we discussed earlier, and 6B is power spectral density of the sequence. So thank you everyone.